this action of R2K minus 1 or R2K give you this semi-product. And you can give this group a Riemann matrix, which is invariant, left invariant, and has this standard one identity. So for any four lattice stable on the representation defines an orientated Riemann submanifold of dimension 4K minus 1. So this is the main object in Herzberg's conjecture. So here, this A is a lattice in R2K, U is a lattice in R2K minus 1. So Herzberg made an amazing conjecture relating the signature defect of this submanifold M to the spatial value of certain L series. So when he needs to compute the dimension of Hilbert module forms, so he introduced this L series. So defined in this way. The conjecture says this signature defect equals this spatial value of this L series at 1 and up to some constant. So this L series has the entire continuation to the whole complex plane and satisfies functional equation relating S and 1 minus S. So now I would like to ask a question. What is the topological meaning of this L series being identically zero? So this L series is a linear combination of L series of Higgs characters. Not only just one Higgs character. And this combination coincides the topology structure. So to simplify the situation, let's just focus on the case of three-dimensional in this talk. The first observation is the following. Let M be a orientated source manifold as in Herzberg's conjecture. LMS is similar to L series. Then this L series is identically zero if and only if M is a chiral. Immediately, namely, it admits this orientation reversing homomorphism. So the sufficient condition is simple. And the second one for non-archival M, this L series is a complete topology invariant for M. So the key fact to have this connection between number theory and topology comes from this basic fact. Any narrow ideal class contains infinite many prime ideals. So once we have this proposition, maybe you can ask, so for archival manifold, what we can say about this? Can we say more on the connection? For the second observation, if this M is not archival, then this L series is complete topology. Then you can have its Taylor expansion, say at S equals 0. Then you can ask the topological meaning for this Taylor expansion, this coefficients of Taylor expansion. So Herzberg's conjecture just tell you the meaning of constant term. But now it's highly unknown, open, the topological meaning of these other coefficients in Taylor expansion. But in number theory, there is a formula of Yinzhiwei and Zhangwei. And so they give this Taylor expansion of certain L series in terms of this height of some cycle. But here we have a similar situation, and we can ask such kinds of question. To prove this proposition, or say how to invite number theory into this topological setting, is the following. So given any this manifold, you can consider this algebra generated over Q by this rho U. So when you restrict U, the rho on U acting on A, so you get a representation, integral representation. So you put this rho U on Q, you get a real quadratic field. Now, in general, you get a totally real field. So if you identify this R2K with this F tensor with R over Q, then you can realize this A as a complete module of F. So it is associated on order of this totally real field. And then you can realize this U as a group of total positive units in F. And this representation is given by multiplication of the units on these elements of F. Now, a key object here is this narrow ideal class group of order O. And let A, this bracket A, denote the class of A, then we can translate the topology meaning of achirality into this in number theory language. So first of all, this M, A1U, AIUI are homomorphism as orientated manifold if and only if these two subgroup of total positive units are equal. And this ideal class of A2 equals the ideal class of A1 up to plus minus 1. If you take elements in F class with norm negative, then there is an order 2 ideal class, zero ideal class generated by this theta. Of course, this is independent of theta. So this play like a central role in the story. Now we know this MAU as a topology manifold is homomorphic to M theta AU, but the orientation reversing. So if this manifold is archival, if and only if this ideal class equals 0 or belong to belong to 2 times this ideal class group. Now the second question. So does there exist a manifold, so manifold of dimension 3, such that any of whose covering is chiral, or equivalently, any manifold comparable with M is chiral? So we can use what we have said to start this question. Here, we introduce some definition. So two manifolds are called comparable if they admit common factor covering. So a comparable class is called achiral if it contains an achiral member. So the question is to ask, is there any chiral class? So first, let's classify this comparable classes of Sol 3 manifold. So it is one-to-one corresponding to real quadratic field. And this Gauss's genius theory answers this question perfectly. So a comparable class of Sol 3 manifold is achiral if and only if there is no prime divisor of this discriminant of real quadratic field and is congruent to 3 mod 4. So this basically follows from the how to say description of achirality in terms of this ideal class theta. So it's very surprising that Gauss's this built work in his book, this arithmetic, so is used here. Now, so what can we say about this connection between number theory and the topology for achiral classes? So this is our question. Among all achiral classes, how does these ones containing a non-orientatable member distribute among all archival classes. So if a class contains a non-orientatable member, then its canonical double cover is automatically archival. So classes containing non-orientatable member are archival. Maybe we can call it spatial archival classes. So the question is asked how spatial classes distribute among all archival classes. So this is the following theorem is our joint work with Wang Shiceng and Wang Zongzi. So the theorem says if we order these classes by their discriminants, so the density of commutable classes containing non-orientatable manifolds among archival classes is 1 minus this product. So it's around 0.50 something. So it's bigger than 1/2. So this distribution problem is closely related to Stevink's conjecture in number theory. In fact, a archival class of discriminant D contains a non-orientatable member if and only if this negative pair equation has an integral solution. And we know this negative pair equation has an integral solution and has the following necessary condition. So any prime divisor of D cannot be congruent to 3 mod 4. If you mod this divisor of D on both sides, then you get this x squared equals -4. So this means -1 is residue square. So this the third condition is obvious. But the density of this D such that negative Baire equation is solvable among all D satisfying this necessary to say this easily. Okay, now for the remaining two ones, this is sole one. We know it has infinite many commutable classes and one-to-one and corresponding to real quadratic fields. And this archival one corresponding to those real quadratic field whose discriminant has low prime factor congruent to 3 mod 4. So spatial one corresponding to those D such that the corresponding negative Baire equation has the integral solution. So then the distribution given by the density, like bigger than 1/2. Okay, so now the remaining ones in three-dimensional case is hyperbolic case. And there are still this infinite many classes. So what's the answer for this case? The distribution problem in hyperbolic case is completely different from Thor case. So this is my joint work with Yin Hang. So in this case, we prove any archival class of closed hyperbolic three manifolds must contain non-orientable manifold. So there is a sketch. So this kind of manifold has the universal covering of three-dimensional hyperbolic space, and it's an isometric group given by PSL2C semi-product with this order 2 group, where this order 2 group, these non-trivial elements act on PSL2C by complex conjugation, and which also change orientation. To show this theorem, so first, it's useful to construct question to extend the question for closed manifold 2 or hyper like 3 orbifolds with fat volume. So we don't require it's compact. And so the reason is the following, because if I give you a chiral gamma, this means this H3 mod gamma is archival. So then you can think about its normalizer. By definition, this normalizer has elements projects to C, so we call it non-orientable. And because this manifold has a fat volume, then you know this normalizer has gamma as subgroup of fat index. So this N gamma and gamma correspond to 2 orbifolds, which are commutable. Now the question reduced to how to find a torsion-free subgroup of N gamma, which has elements projects to C. This is a number theory question. Looks like so it can be solved using strong approximation theorem with respect to this invariant field and the quaternion algebra of a chiral class. So the proof is quite subtle. Now, so for the distribution problem of spatial classes, we now have a better understanding in three-dimensional case. How about the higher dimensional case? So we expect higher dimension case will involve much more connection between number theory and the topology. For example, if you just consider this Thor manifold in Hertzberg's conjecture, which has dimension 4k minus 1. So let's just think about a very special case. If we require the relevant total real field F is Galois over Q, with the Galois group isomorphic to is the abelian group of exponential 2. For example, just this. Then the corresponding distribution problem in number theory is much harder than what we said we saw for this Stevens conjecture. So even for G equals 2 is highly non-trivial. And also, this kind of problem involve this two-adic mathematics in number theory, and which has many similar situations in number theory. So now at the end, let me give you one example to see how this kind of distribution problem look like. So let's recall, if a positive integer is called a congruent number, if it is the area of a right triangle with rational side length. So there is a result about the congruent number. So for a density 1 so there, sorry, the English has something wrong. So there is a density 1 subset of square-free positive integer n congruent to 1 or 3 mod 8. And you look at this dependent equation, x squared plus 2y squared plus 8z squared equals n. So think about its integral solution. Now, the number of solution with z odd is different from solution with z even. So this kind of n has density 1 among all positive integers n congruent to 1, 3 mod 8. So the proof of such a result involves this kind of two-adic number theory on this two infinitesimal group of corresponding the elliptic curves, and then use this use the result on BSD conjecture. They call the two converse, P converse for those curves in rank 0 case. Then finally we can get this kind of Goldfield conjecture for congruent number. And we believe such kind of connection also maybe happened in this topology situation. Okay, so this is my talk. 最后出现在第二盘。
Any questions?
Yeah.
Yeah, sorry. I didn't follow how the certain geometry arised from your.
Okay, we start one spatial example, this Saul case, among this 8 geometry. Right. And so for this Saul manifold, there are some non-orientatable, and even for orientatable ones, some of them are achiral. This means they admit homomorphism change orientation. So when we think about this related, the Shimizu error function, then we found the error function identical to 0 is exactly equivalent to achirality of this kind of manifold. Then, but Herzberg's conjecture say nothing in this case, right? So because this Herzberg's conjecture relates its spatial value to some geometry invariant. But if it is identical to 0, so then it's nothing. It's very easy to say the equality holds, both sides are 0. So we ask ourselves, what can we say for achiral ones? This means this number theory object, L series, are identical to 0. So we found that it's very interesting to think about the distribution of subsets of achiral classes which are non-orientable. So it is related to this classical pair equation problem. So we found this density. This density has a very similar distribution problem in BSD conjecture for elliptic curves. Then you can ask, what's the generalization of this problem? So it seems to us, if you fix the geometry model, then this number theory is naturally coming into the picture. But if you put this 8 cases think about it together, it's not so obvious. So then we think about the remaining 7 cases, but there are 6 trivial ones. The only non-trivial remaining ones is hyperbolic case. And again, this kind of fix the geometry model tell you this strong approximation story coming into this case. So it's again about this two-adic stuff. Then we think about in general, if we fix any geometric model, can you ask the same question and expect more number theory come into the topology questions? So in other words, this geometric model gives you more number theory.
More questions? If not, let's thank Ye again.
Thank you.
Next talk is in 3 minutes.
Sorry, okay.
In